Good evening and welcome to this webinar presented by the IET's Cambridge Network. We represent members in the Cambridgeshire area, but we're very pleased to welcome folks from around the UK and indeed globally tonight. My name is Phil Zangast. I'll be your host this evening. I'm the chair of the local network. Before we get underway, I'll just cover a few housekeeping points. We'll leave questions to the end of the event, so if you think of something during the event, please use the Q&A button, and you'll find the Q&A button down at the bottom of the screen. If you wiggle your cursor on the Zoom control panel, it will pop up. We can't answer any questions posted on the using the chat button. We'll try and answer all the questions tonight, but our speaker has offered to answer any questions that are left over offline, and we will post those on the IET Cambridge website. And we will be recording the event tonight, and you can find the video on our new YouTube channel, which you'll find by looking for IET Cambridge on YouTube. Finally, I'd just like to mention our next event, which will be on the 25th of February, and that will be on the subject of aircraft electrification. Now, on to tonight's speaker. And I'm very pleased to welcome Steve Baker. Steve works at TTP, which is a Cambridge-based consultancy, and he spent 30 plus years working on mobile wireless communications. Steve has a master's degree in electronic engineering, and he's developed technologies, products, and businesses used in that sector. Those have delivered test systems, radios, protocol stacks, and application platforms across the mobile phone networks. So I'm very pleased to hand over to Steve Baker. Thank you.
Steve, we can't hear you.
Can you hear me now?
Yes, we can.
Good. Okay. Wireless technology is fine, but pressing buttons, far too tricky. So good evening, everybody. Sorry for the full start. Phil, thank you for that introduction. Let's get underway and see if we can chat about what is so interesting about 5G. Okay, have my slides appeared?
Yes, they have.
Excellent. Okay, then let's crack on. Right. Yeah. Okay. Good. Right. So plan them for the next 30-35 minutes is to have a quick cellular systems primer. Look at the 5G design goals. There are three key design goals, which are often referred to as the pillars of 5G. And then we'll look at some key implementation topics which stem from those goals. In the blurb for this event, I noted that there is no such thing as a free lunch. So 5G is going to be marvelous, isn't it? But who is going to pay for that? So we'll look at where the impact of the 5G features are really going to be felt. Have a quick look at the current status and of deployment in the UK, and then have a look at what's next. Now, I'll give a quick personal introduction by way of context, but while I'm doing that, Phil, could I ask you to publish the two polls, please? There's just a couple of polls. One to help me understand the demographic we have here today, and the other just to gauge people's familiarity with the sorts of technologies that are going to crop up.
Steve, everyone should be able to see the polls now.
Great.
Just to briefly read those out. First question is: do you follow do the following terms mean anything to you? FDMA, TDMA, CDMA, and OFDMA. And second part option is Shannon, Viterbi, Turbo, and LDPC. So we'll just wait a moment for people to vote. And I think we're pretty much, still a few people voting. Okay, there's some people saying that neither are familiar. So,
Excellent. Excellent. Okay, that's fine. So I shall do my utmost to bring everyone along. That's great.
I'll end the poll there,
Okay.
and then we should be able to see the results now.
Good. Great. Okay. That's good. I'm looking forward to that then. Thank you. And could we do the other poll as well, Phil? Just the
Sure. Bear with me a second.
Great.
Oh. Okay, sorry about that. You should be able to see the poll now, everyone. So this is looking at giving Steve an idea of the demographic. Have you ever made a phone call on an analog mobile phone, or made a call on a 5G mobile phone, or made a call on both types of phone, or none of the above?
Actually, that was meant not to be a multiple choice. That was meant to be a single choice, really. But hopefully we can interpret the answers.
Some people are having problems putting in none of the above, but looks like we're getting a fair number of votes against those options. So I will end the poll there. And then share the results.
Well, I'm impressed and entertained that almost 2/3 of us, 59% of us, have made a call on an analog mobile phone. Not so much on the 5G front, but also nice to note that the 5G phone users were almost all analog phone users as well. Good. So I am just old enough to have made a phone call, only one, on an analog phone, back when I was at university, and I catched a lift with a glamorous friend of my parents and used the phone in their car. Phil has already mentioned I have a background in electronic engineering. Started developing test and measurement systems for GSM devices, working for Marconi Instruments, who were just opposite the IET building on Six Hills Way in Stevenage. And I then product managed 2G, 2.5G, and 3G protocol and chipset developments for mobile devices. I was working for a business that was acquired by Motorola, and so I spent a couple of years inside Motorola doing mobile application work. And then moved to TTP, where I work today. And I did a couple of years ago put together an LTE small cell proof of concept device to create a small cell for deployment on street lamps in urban environments. I don't, however, have any 5G technology to push to you, so I just have a keen interest in the topic, and I'm sort of familiar with cellular, and I'm watching with interest what's happening in 5G. So there's the background. So now let's look at cellular operating principles and a quick look at all the Gs. So given that most of you are familiar with TDMA and FDMA, TDMA, CDMA, and so on, I guess you're probably also fairly familiar with cellular systems. But what we're illustrating here is a bunch of base stations, so a bunch of radio towers, which transmit and receive signals in mobile phones and are coordinated via a network core. That network core connects through to the PSTN, the public switched telephone network, and to the internet, so that voice and data can be routed out to wherever it needs to be routed, or in or out. Important things to note then, that each mobile device is looking at as many base stations as it can see and is communicating with the core network to describe its own perception of the radio environment, so that the network can route calls in the most efficient way, or route traffic in the most efficient way. Over the years, the terminology has changed. BTSs became eNode Bs, and core networks acquired lots of new functions as we moved from voice to packet data, and then from voice plus packet data to all IP. But that is the essential model that we're talking about. A set of UEs that terminal devices that roam freely and move from one base station to another as their service demands change. All right, all the Gs, quick whiz through this. You know that we have a new G every decade. So if the 80s were the period of 1G, I put that in quotes, of course, because when 1G was delivered, it wasn't 1G, was it? It was just what we had. We didn't know it was the first of a line. The 90s saw 2G and 2.5G. So I worked on GPRS and was very excited to see as much as 100 kilobits per second of data trundling out of my 4-slot GPRS devices. 3G delivered much better data rates. 4G, typical data rates measured in the UK today, about 35 megabits per second. Of course, depends where you measure, but in urban areas. 5G is available today in the UK. We'll talk about that later. 150 megabits per second is an entirely realistic throughput to achieve from these devices today. So the story has been voice and text, voice and data, voice and more data, even more data, even more data. That's been the story. But is 5G really more data, or is there more to it? So we'll, in a moment, look at the 3 pillars of 5G and see what the story is. Just one small aside. I have a colleague who lives in the Fens, and of course we're all working from home these days, aren't we? 4G in the Fens is better than ADSL. It's quite impressive. Okay, so the design goals, the 3 pillars, and I'll introduce a conundrum as well, just to keep it interesting. Pillar number 1, enhanced mobile broadband, or EMBB. Please don't blame me for the curious typography, the lowercase e and capital MBB. That just comes from the standards. The goal is that 5G should deliver 10 gigabits per second to a user in the downlink, so from the network down to the terminal. Should deliver 10 gigabits per second in the uplink from the terminal to the network, and 20 gigabits per second from the network down to the terminal. And there's an expectation that you should expect 100 megabits per second typical throughput in an urban environment. And typical is defined as 95% of the time. So I think that's quite a nicely drawn objective, actually, because we know that wireless networks often disappoint, and you know the advert says it's marvelous, and the reality isn't there. But I like the way it's framed, that 95% of the time you should, with a well implemented 5G system, get 100 megabits per second. The next one is ultra reliable, low latency communication. So the goal here is to achieve 5 nines reliability. So that's almost Ethernet levels. Ethernet aims for 6 nines reliability, but 5 nines reliability and 1 millisecond latency across the radio interface. Why the picture of a B? I don't hear you ask, of course, because I can't hear you. But why the picture of a B? That B is buzzing at about 250 hertz. So at 1 millisecond latency, in the time it takes for the B to beat its wings once, we could transmit from A to B not to that B, of course, to a different B. We can transmit from A to B and back again twice in the time it takes for that B to flap its wings once. So I think that's to me is an extraordinary encapsulation of the technical challenge that's being set there. The other type of communication, the other pillar is known as massive machine type communication. The hyphen is important, of course. This is not communication for massive machines. The way I interpret this is we want to deliver machine type, so IoT type communication at a mass scale. And just to put this, to be specific, the goal here is that a 5G system should be able to support 1 million users in a 1 kilometer square. So in other words, 1,000 meters by 1,000 meters. So at every meter interval, you should be able to place a device and your 5G network should be able to talk to all of them comfortably. Now this, okay, so that's the essence of it. I guess on this point, worth noting that effectively 5G is just importing the NB-IoT specification, which sort of goes right back to GSM territory, and the CAT-M IoT specification, which comes from the LTE standards. It's just importing them lock, stock, and barrel and fitting them into the 5G radio interface, as we'll see presently. MMTC, I think, is really impressive. It supports far higher density than unlicensed LPWAN systems like LoRaWAN, and it offers a link budget of 164 dB. So actually, that's delivering probably a better link budget than you would get from a LoRa type system. So it's really impressive. What was the conundrum? Well, there are some sort of very contradictory priorities here. MMTC, so for that IoT type communication, I have very small payloads to send. So I want the setup time to be as small as possible. I want really efficient session setups. And I want to be able to sleep very, very deeply for all the time that I don't want to communicate with the network. EMBB, the ratio of setup to payload, it almost doesn't matter because the payload volumes are going to dwarf traffic by a mile. So there are quite different implementation priorities there. And URLLC, that to me seems inherently contradictory. I want to be very reliable and have very low latency. If I want to be very reliable, I might buy myself a bit of latency so that if a transmission should fail, I have time to retransmit and maintain my traffic stream. And I've just flexed by allowing a little bit of latency. But actually, we're setting our stall out here to do both, which again is quite challenging. Right, key implementation challenges. Spectrum utilization, channel optimization, and network slicing. Spectrum utilization, I'm talking about making best use of the spectrum that's available, or my analogy here is packing the car for a camping trip. And channel optimization, I'll try and explain by reminding you what drinks parties were like from the days before lockdown. And network slicing, I'm just going to describe to you as it is because I couldn't think of any diverting analogy. Okay, we want to use the spectrum we've got efficiently. Imagine the boot of this car is the spectrum that we can use for transmitting and receiving in our cellular system. We can share that spectrum in a number of ways. So I'm going to imagine that's the frequency across the back of the car, and I'm going to pretend that each suitcase represents a frequency channel. So go back to the analog system. 25 kilohertz FM channels were given. So if you wanted to talk to someone, you were given a 25 kilohertz channel to talk on and another one to listen on. And your neighbor was given the adjacent 25 kilohertz channel and so on. Quite inefficient because of the gaps between the channels. And actually, these suitcases are not very efficiently packed because, of course, there are physical gaps between the suitcases as well. Actually, for an efficient packer like me, I need about a quarter of a suitcase when I go on holiday. So it's particularly wasteful if you have to allocate a whole channel to someone who doesn't really need all of that channel. So step one, we could use bigger suitcases. And then we have fewer gaps between the suitcases. We use wider channels, and we'll have fewer what's called guard bands between the channels. And so when GSM was introduced, we went for 200 kilohertz wide channels. So 8 times, the channels were 8 times as wide, but we got 8 people to share that channel, which doesn't sound like an advantage yet, does it? But we'll come back to that in a moment. When CDMA came along, we actually said, look, we'll just have one suitcase, and everyone can share the space inside the suitcase. We'll get multiple people to pack per suitcase. By the time 5G has come along, and we use a system called OFDM, where we create sub-channels inside the allocated frequency. We can really, really efficiently share the resource inside that suitcase. So I would just need the little netted bag on the inside for my stuff for the week, and the family can take the rest of the suitcase. In 5G, we talk about, or 4G and 5G, we talk about resource blocks, so very small allocations of frequency of these digitally creating sub carriers and time slices, which can be allocated with very fine-grained control to different users. So we share in frequency and in time in a very fine-grained way. There is no, when we do it digitally, there's no guard band wastage in the middle between these channels. And we also do things like forward error correction. So to make most of every bit we send a few extra bits which will let us find and fix errors on the way. So in 2G we used convolutional codes and Viterbi decoders. In 3G and 4G we used turbo codes. In 5G we moved to something called LDPC, low density parity check, which is sort of like a turbo code, but it requires slightly less processing to do the decode. And when you have very, very high traffic throughputs, 100 or 20 gigabits per second, the processing overhead of checking with LDPC is lower than with turbo. There's a slight processing gain, but not a whole lot. So in 4G and 5G, we end up with the notion of a resource block. We can slice up this resource block, which is 180 kilohertz wide, 1 millisecond long, might have just 12 or as many as 96 bits of data inside it. But we have a super flexible scheduling scheme to pass these bits around. So by the time you're looking at the boot of a 4G car, that's how you're packing the data in. There is no wasted space in there. This is a good time actually to now think about spectrum allocation itself. So we talked about using the spectrum we've got efficiently. How much spectrum have we got? Actually, when we go to 5G, we're not dealing with the boot of a car. We're dealing with a whole recreational vehicle all on its own. I'll give you real numbers in a second, but to illustrate this is just to illustrate the point. There are loads of spectrum is made available for 5G, which is why some of these high rate services can be delivered. I thought this picture was particularly apt because, as I said earlier, 5G is just enveloping the NB-IoT and the CAT-M specifications for IoT services directly into 5G. Using those flexibly allocated resource blocks I just told you about, you can just pop an existing NB-IoT or CAT-M service into the 5G resource block structure, and you go away. So we can park our 4G network inside the 5G network, as illustrated by this RV here. What does it really look like in spectrum allocation terms? We have all the sub gigahertz that we're familiar with from 2G, 3G, 4G. A lot of 4G goes up to sort of 2.6 gigahertz today. There's a lot of allocation for 5G up to or below 6 gig, and especially around the 3.5 gig mark. And then we're allocating millimeter wave spectrum, so up at 26 gigahertz, which is far higher than has been used for any cellular services until now. Bear in mind, a single 5G radio channel can be wider than the entire spectrum allocation that was granted for the 1G and 2G services. So analog tax that we had in the UK had 625 kilohertz channels in each of the uplink and downlink. So a total of 30 megahertz was allocated. And 5G specifies channel bandwidths of 5, 10, 20, 40, 80 and 100 megahertz. There are hundreds of megahertz allocated, contiguous bands allocated in the 3G domain, 3 gigahertz domain, and there are units of gigahertz allocated up in the 26 gig area. So just talk about spectrum for a second. The analog cellular licenses were sold for £25,000 back in 1982 to what was then Raycal and BT. 16 pennies per hertz, I think, that amounted to. US operators have just finished bidding for the 3.8 gigahertz, so band C spectrum in the US. They have paid $80 billion, that's with a B, $80 billion for that spectrum. It's quite stunning, isn't it? Right. We've got our spectrum. Thank you, and we're using it as efficiently as we know how, with our resource block, fine-grained control of resource blocks to share it out to all the users that need it. So what's next? So the next challenge is channel optimization. So let's talk about drinks parties. This, of course, is every drinks party I've ever been to, as I'm sure you can imagine. The radio environment is often interference limited. Although we talk about link budgets in terms of absolute noise floors, often really in a cellular context, interference is the problem. Interference from other users. I guess to misquote Sartre, hell is other users on my frequency or in adjacent frequencies. Now, we see this at a drinks party. You turn up early, as I would, unfashionably early, and you can greet your host easily as you wander into the kitchen, and you can hear them greet you, and they can hear you reply. But a couple of hours later, as the room is filled and glasses have been downed and voices have been raised, it gets a bit harder to hear and to be heard. But I notice as I get older, I tend to remove myself to the fringes of these things, because, and not because of the innate shyness that led me to engineering in the first place, but because things are quieter at the fringes and it's easier to hear. A hand behind the ear helps, doesn't it? Of course, you know that. That's helping for two reasons. It's capturing the voice coming towards me, and actually it's shielding the voices behind me that was making me struggle to hear the person I was talking to. Now we have exactly the same challenge here in a radio context. We want to not be deafened by the person next to us. We want the person we're talking to be able to hear us clearly. And so we use a system known as MIMO, multiple in, multiple out. So this is a system where at each end of the link, you have more than one antenna and more than one receive chain, and more than one transmit chain. And by placing the antennas more than a quarter of a wavelength apart, you have the possibility of establishing discrete radio paths. You know that you generally don't see a base station when you're on your phone. You're not looking at a base station. You're actually receiving reflected signals, and you're receiving reflected signals from multiple directions. So what this works at a number of levels. So at the simplest level, I can just have under my own control 2 receivers, 2 antennas, more than a quarter wavelength apart, and I can receive on both of those antennas, and I can make a judgment as to which is giving me the best signal, and I will simply choose to use the best signal, whether I preferentially select one over the other, or whether I combine them in some proportionate way. That doesn't matter, but I can be sure that I've got at least the best signal possible that way. Taking it a step further, if I've got reasonable signal to noise, actually I could establish 2 separate radio paths. If I've got separate reflected paths to get me to those 2 antennas, I could I could take advantage of that potentially, and with a little bit of connection end to end, communication end to end, a bit of negotiation, we could establish two radio paths which are spatially separated, even though they're operating in the same frequency. This requires a whole lot of processing. It requires me to understand the channel and the phase and amplitude distortions that have taken place in the channel. But if I can understand that, then I could correct for it, and I could end up with I could end up with two viable independent received signals. We can take this even further. So 4G and 5G both offer the idea of channel sounding bits, so that we can read the state of the radio link to understand what the gain and phase variations are on the paths that are being received at these different antennas. And we have the notion of massive MIMO, where we now have many antennas, maybe 64 antennas at each end, and particularly if you're using a single frequency system, a time division duplex system, where everybody transmits and receives at the same frequency, the base station can read the channel state information bits that it receives, understand the state of the channel to every device it's talking to on every one of its antenna paths, and work out how to pre-distort or pre-disperse the signals it transmits across each of its antennas, such that the signals, when they eventually arrive at its target device, will all be nicely aligned, and you'll have a really high quality, what's called a hardened channel. You'll have it's as if you've gone down a perfect link. And there's games to play then around, do you go for one perfect link, or do you go for multiple spatially discrete links? But it's a really powerful technique. It is the equivalent of your party host running around and making sure that as people chat, the people who stand back to back should speak simultaneously, and the people who stand side to side should take it in turns to talk to minimize the interference. So when you get to this massive MIMO state, not only can you design the transmission pattern to deliver a clear signal to your intended interlocutor, you can also deliver null signals. So you can make the antenna pattern a null for all the people with whom you might otherwise interfere. So it's really a phenomenal technique. Of course, it requires huge amounts of processing power to make it work. I've just lost my mouse. It's interesting. Forgive me for that. I'm slightly flying blind now. Anyway, we're looking at now network slicing. So we've talked about utilizing spectrum efficiently, maximizing our use of the channel, so optimizing the channel using MIMO techniques. And now we're just going to talk about network slicing. So I said that the bits and pieces within the network have changed name over the years, but the essential functions are all much the same. That is true, but there's a philosophical difference with 5G, and that is that network functions are virtualized. There are no dedicated 19-inch racks containing your HLR or your MSC or your GGSN. These now are just lumps of software that run on a server somewhere. That's important point number one. Important point number two, go back to the point about resource block allocation. You know, we have really fine control over all the resources, over all the physical resources at the edge of the network. So what's referred to as the access network. And we have a virtual network core. So with the aid of an orchestrator, we can have multiple network cores, which are themselves tailored for different purposes. And they can be allocated a slice of resource in that access network, so that you can run a network core optimized, for example, for IoT, our blue cloud here, and one or more of those base stations, it's in the gift of the network operator to decide. One or more of those access networks or base stations could allocate a certain amount of resource for IoT type functions, for those MMTC services. Some of the resources on those gateways, on those access networks, base stations, could be allocated for mobile broadband and others for critical communications. But it allows the operator to create application-specific networks, and it lets devices connect through the common infrastructure, through the one access network, but through the slice of that access network that's dedicated to mobile broadband in this case, or is dedicated to IoT in that case, or is dedicated to critical communications in this third case. So it allows an operator to run a public mobile broadband service, for example, and at the same time use those base stations that it's deployed for the public to run a critical communications network for the police, fire and ambulance services, but run it in such a way that there's absolutely no interference between the two networks. No way that the public mobile broadband network could take resources away from the safety critical network. It also, because going back to spectrum allocation, there's a lot of unlicensed spectrum available. So unlicensed spectrum is available, and network deployment is now a very flexible beast, and it really opens up the opportunity for unlicensed or non-traditional network operators to get involved and start operating services. And I think that's something we'll see increasingly in this domain. Right. I'm aware time is against us, isn't it? So who's paying for lunch? Spectrum allocation. We've said high frequency allocation for those fast services because lots of spectrum is available. But when you go up in frequency, especially when you go up to 26 gigahertz, everything gets expensive. The power amplifier, which costs you cents at 1 or 2 gigahertz, starts costing you dollars and even tens of dollars as you get up to 26 gigahertz. And as you go up in frequency, the propagation range tends to fall off. And so base stations will have reduced range, especially at the highest frequencies. So that sports stadium we saw, yes, everyone can have their 100 megabits per second, or 95% of them, but we will need to put a lot of small, high-frequency base stations in that sports stadium to make that work, and we will have to wire a lot of fiber around the stadium to connect each of those base stations. So base station footprints become smaller, and the infrastructure to support them becomes more expensive. Radio complexity is also an issue. So MIMO is fantastic because we can literally get two radio transmissions between two endpoints. We can get two separate, spatially separated radio paths. So that is fantastic. That really drives up the efficiency of the network as a whole. But there's a real cost in terms of the transceiver chains because you now need a transceiver chain behind every antenna to make that work. That said, the volume market will drive integration and cost reduction. It's happened with every G to date, and it will continue to happen, I don't doubt. Signal processing complexity is a challenge. So that channel optimization, especially the massive MIMO, is so computationally intensive. The system architecture places most of the burden on the base station. So the base station can do the channel sounding, but because everyone transmits and receives on the same frequencies, the channel is reciprocal. It looks the same in both directions. So the base station can do all the work for the mobile device, which is a smart configuration. But if you have a 10 kilowatt base station, it's going to have to be water cooled. Someone described these as hungry hippos. I thought that was a nice little irreverent term for it. But you can expect very high power consumption from the base station. The processing problem is taken care of by Moore's law, in a sense. Processing power has increased manifold over the years, and will continue to keep pace, I guess. Okay, I'm sorry, I'm very conscious of time, so I'll scoot along. So let's look at current deployment status. First thing I want to look at is, right, look at the right-hand side first, handset premium. Pixel 4a 5G is a very current, newly launched phone. Pixel 4a is pretty new, it's less than 3 months old. There is a 43% premium on price to get the 5G version. So that means it's a 400 quid device instead of a 350 quid device. Motorola will sell you an entry-level 5G device for 250 quid. Actually, I think that's not very expensive, really, especially when you imagine when you think about the scale of processing power and radio complexity that these devices embody. A little before and after comparison. So in 1995, a voice-only phone would run on a 20 megahertz I186 type CPU, 1.5 million transistors on a half micron process. 15 years later, Qualcomm's current 5G chipset, which supports 7.5 gigabit per second on-air data rates, is built on a 7 nanometer process, 10 billion transistors, has 8 2.8 gig cores. It also supports GNSS and 8K video. But that is the demonstration, I think, of Moore's law, delivering the processing power that's needed. There is a cost. I guess maybe I should have said who pays. There is a cost in power consumption. If you're doing a voice call on a 5G device, it will burn the battery more quickly than if you were doing it on a 4G device or indeed on a 3G device. That is a fact. But you're not going to get those data rates without using more energy for now. What does it look like in the UK? There are over 100 UK cities and towns. Must be cities and towns, because I'm sure we don't have 100 cities in the UK, do we? 100 population centres have 5G service. Point Focus conducted some speed tests last year. Right up and down the country, they have a really dense network of test sites, and more than 70% of speed tests conducted in September 2020 delivered better than 100 megabits per second. I think that's quite impressive. I was quite encouraged to read that. The little chart actually shows you the mean the mean UK-wide throughput and the max London throughput for the 4 5G operators that we have here. So mean throughput of 150 meg for 3 of them. And there's good handset supply. There are plenty of manufacturers today offering affordable 5G devices, which again I think is quite impressive. Where do I think this will go in the future? What's next? So I'm sure we're going to see 5G deployed for industrial IoT and for Industry 4.0, as it's called, functions. So there's a lot of IoT going on today. Projects I have worked on in IoT, if I was to start them again now, 4 or 5 years later, rather than using LP WAN, I would most definitely be considering cellular options. Industry 4.0, 4.0, there's a lot of talk of flexible factories and factories that are sort of quite dynamically reconfigurable. When you have that kind of factory in mind, then wired infrastructure, so wired Ethernet, starts to sound a bit painful. And at that point, the RLC option of 5 nines, if not 6 nines, reliability and millisecond latency for a factory network sounds really quite interesting. And bear in mind that this can be delivered by either as a network slice from a mainstream operator or as a private network. Then I think there's interesting potential there. I think smart cities are also an interesting area. Transport, lighting and energy, the all obvious IoT type domains. But I think that V2X becomes really interesting too at this point. So this is the idea of vehicle to infrastructure communication to make vehicles more intelligent as they navigate cities, to communicate with roadside infrastructure, for example. And I note that in the US this last year, the FCC has removed the spectrum allocation that was given to the DSRC, so digital short range communication services for automotive V2X type functions. So there was some 5 gigahertz spectrum allocated to that in the US. That has been deallocated because the automotive industry didn't move quickly enough to really achieve anything with it. And there is a chicken and egg problem here. Who wants to invest in proprietary infrastructure for a city when there are no vehicles to use it? No city can afford to invest in that. Who's going to pay extra to have the V2X functions in their car if there are no cities within which to use that paid for feature? Whereas V2X delivered over 5G has the potential to deliver the reliability that's needed, but the infrastructure is paid for in effect by the commercial deployment of mobile broadband for the consumer population, and you can then create a slice, so protected, secure, and untroublable little radio subsystem for the V2X functions using all these standard protocols. So I think that's got, has it got legs? It's got wheels, I suppose, hasn't it? But there's real potential there, I think. I think there's some opportunity for critical communications. There is the use of LTE for critical comms has struggled because it's almost perfect, but the critical services sector requires some changes to the standard. And as soon as you require some changes to the standard, it's no longer standard, and it doesn't come with all the cost benefits that you expect it to come with. And so using a commercial technology suddenly is less attractive. But because of the flexibility that 5G delivers, and because of the performance it delivers, the two combined, and because it enables non-conventional operators to participate, again, I think there's a huge opportunity here as well. Actually, there is one other, which is fixed wireless access. Very high broadband stuff could replace a microwave, a millimeter wave could replace a lot of ADSL and fiber broadband. But I probably ran out of time, for which I apologise. But I think that's also a potential application area. Okay, let me stop there. I'll stop sharing, and of course I'm happy to try and address any of the questions that you might have sent to David. Thank you.
Thank you, Steve.